Right. Right. We'll start. Now today we are starting unit 3, simple harmonic motion. Now talking about unit 3, it's very long unit as mechanics. So when you are syllabus, unit 2 and unit 3, they are the longest units in your syllabus. Right. So when talking about unit 3, now comparing with mechanics, the concepts and theories in unit 3, they are somewhat unfamiliar. So therefore, but I try my maximum to explain everything with my best. So what you want to do is, every day, don't miss any single class. Come every day. When you join for a session, keep your 100% attention until class finishes. Right? So today we are starting simple harmonic motion. So everyone put your new unit 3, oscillations and waves, subchapter simple harmonic motion. Start writing. Unit 3, oscillations and waves, simple harmonic motion. Simple harmonic motion. Subtopic periodic motion. Subtopic periodic motion. Subtopic. Now, first of all, we'll write note, then I will explain what is periodic motion. Write down. Write down. A motion which repeats. A motion which repeats itself a motion which repeats itself, a motion which repeats itself at equal time intervals. At equal time intervals is defined as periodic motion. Is defined as periodic motion. Right, okay. Wait a minute. So wait for a minute. Right. Uh, So connection is not stable, right? Give me 1 minute. Right. Now I think it's all right, right? Okay. Right. Now, first of all, you want to understand what is this periodic motion. Now, periodic motion means what? If an object repeats the same motion again and again. What is periodic motion? If an object repeats the same motion again and again, that type of motion we are calling as periodic motion. For an example, now you know what is simple pendulum. Motion of simple pendulum is a periodic motion. Why? If I draw simple pendulum, very carefully listen. Let's say initially my simple pendulum is at a position exactly like this. So when I release this pendulum, we know that what will happen for the motion of this pendulum? This pendulum will move like this, right? This pendulum will be moving in this way, and it reaches this position. Again, it comes back to the same position again continuously. When I release the simple pendulum from this position, the motion of the simple pendulum will be in this way, right? Then it comes to initial position again. Continuously, it's moving in this direction, coming back to initial position. So what happens? Simple pendulum repeats the same motion again and again. So therefore, we call motion of the simple pendulum is a periodic motion. Why? This pendulum repeats the motion again and again. It going to this direction, coming back to initial position, again going back to this position. Motion is repeating. So this type of motion we are calling as periodic motion. Example number one. Example number one. Simple pendulum. Example number one. Simple pendulum. Draw this diagram. Simple pendulum. Now, any other periodic motions? Any other examples of periodic motion? Next example is oscillation of a mass tied in a string. Second example, oscillation. Draw this diagram. Oscillation of a mass tied in a string. Sorry, tied in a spring. Tied in a spring. Let's say vertical spring. Vertical spring. Let's say now there is a vertical spring. There's a vertical spring. Then you tied a mass simple limb at one point of the string. This is your mass simple limb. You tied simple limb mass exactly at the one end of the spring. Mass simple limb. Right? When you stretch the spring to this position and when you stretch the spring up to this position and when you release it, what would happen? Right? When you stretch the spring up to this position and when you release the spring, if not when you release the object, what would happen? This simple M mass will be moving up and down continuously. Then when you consider motion of simple M mass, this simple M mass follows same motion again and again. Going upward direction, coming down, going up and down, up and down. This simple M mass repeats its same motion. So therefore we can say simple M mass moves in a periodic motion. This example.
Excuse me, sir.
Example number 3. Third example. Motion of a glass ball released on a glass ball. Motion of a glass ball released on a glass ball. Released on a glass bowl. Now look at here. Now let's consider a glass bowl. Bowl කියන්නේ මොකද්ද මේ? Something like this. This is a glass bowl. Now let's consider now there is a ball. Initially that ball is somewhere here. Exactly at this corner. When you release this ball, what would happen? This ball keep on moving like this, right? This ball will reach a maximum position somewhere here. Again, come back to same position. So what happens? This motion continuously occurs. This ball will move along this path and reach a maximum position, and then come back to the initial position. This motion continuously occurs, continuously repeats. So we can say motion of a glass ball released on a glass ball is a periodic motion. Quickly. Now I would say that now, please you guys don't join through two devices, right? Only join from one device, right? So raise your hands. How many of you finished writing these examples? Raise your hands. Finish writing quickly. Yes, many finished. Okay. Then you know that now what is the idea of this periodic motion? Now, simple idea is if an object follows a same motion again and again, we say that that object is undergoing a periodic motion, right? I think you understood. Now write down. Now write down definition of simple harmonic motion. Definition of simple harmonic motion. Red color pen. Red color pen. Write down. It's very important. The acceleration acting on a moving body Red color pen, write down. The acceleration acting on a moving body is always directed towards directed towards an equilibrium point and its magnitude its magnitude being directly proportional to the displacement being directly proportional to the displacement being directly proportional to the displacement. From the equilibrium point, come on, then that motion of a body, then that motion of a body is called as is called as simple harmonic motion. Is called as simple harmonic motion. Now please acceleration, highlight acceleration directed towards equilibrium point, magnitude directly proportional directly proportional displacement. Now, okay, now I'll ask one important question now. Currently, you learned different types of motions. First, you guys learned that linear motion. Then we learned about the circular motion, right? Then we learned about rotational motion. Now we are going to learn about simple harmonic motion. If I ask you, every motion has its own characteristics. Now I'll ask a question. If you know the answer, leave a reply. What is the important characteristic in linear motion? What is the important characteristic in linear motion? Leave a reply. In linear motions, what is the important characteristic that we learned? Anyone? Linear motion, what is the important characteristic? Constant acceleration. Very good. In linear motions, acceleration is constant. That is the very important characteristics. Linear motion, acceleration constant. This is what we call as the important characteristic is constant acceleration. Constant acceleration. Then when we learned circular motions, what is the important characteristic in circular motion? What is the important characteristic that we learned for circular motions? Any idea? Leave a reply. In circular motions, what is the important characteristic? What is the important characteristic in a circular motion? Any idea? Anyone now? What is the important characteristic? Circular motion, important characteristic is always understand tangential velocity. When object moves in a circular motion, at any point in the circular motion, object's tangential velocity always perpendicular to centripetal force, if not always perpendicular to centripetal acceleration. In a circular motion, the important characteristic is always understand centripetal force, if not centripetal acceleration, perpendicular to tangential velocity. That is the important characteristic in circular motion. Then what is the important characteristic in simple harmonic motion? Very careful listen. In simple harmonic motion, SHM, simple harmonic motion, and the definition says that, just read the definition. It says that the acceleration acting on a moving body is always directed towards the equilibrium point, and its magnitude being directly proportional to the displacement from the equilibrium point. Then that type of motion we call as simple harmonic motion. Let's consider, suppose if an object moves in a simple harmonic motion. Look at it. Suppose if an object moves in a simple harmonic motion. Now there is an equilibrium point. Okay, now I will explain what is equilibrium point later. Now let's say now there is an equilibrium point. I say that is point capital O. This we are calling as equilibrium point. Equilibrium point. Right? Always, what it says that acceleration acting on this object always directed towards equilibrium point. So no matter when this object moves in a simple harmonic motion, its acceleration direction, this object's acceleration direction always must be towards the center, always must be towards the equilibrium point. Then, so no matter this object moves to the right side direction, no, this object moves to the left side direction, acceleration of this object must be directed towards center, right? Let's say when this object is somewhere here, no matter where is the object, always acceleration at that instant must be towards the equilibrium point. Must be towards the equilibrium point. Towards. Right? This object can be moving this direction. If this object can be moving in this direction, no matter whatever the direction object moves, always if an object's acceleration is to the center, and also if that acceleration is proportional to displacement measured from equilibrium point. Let's say when this object is somewhere here, displacement measured from equilibrium point capital O is, I say simple x. Displacement, I say simple x. Simple x. When this object is at here, displacement measured from point capital O, I say displacement is simple x. Then that acceleration is directly proportional to displacement. Very careful understand. What is simple harmonic motion? If an object's acceleration direction always acting towards the equilibrium point and magnitude of the acceleration at any instant of the motion directly proportional to displacement That type of motion we are calling as simple harmonic motion. Raise your hands, how many of you understood the definition of simple harmonic motion? There are two conditions. First condition is always, no matter any position in the motion, if object's acceleration is to the center and that acceleration proportional to displacement, then we call that object is under simple harmonic motion. Raise your hands, how many of you understood what I explained? Understood. Raise your hands, how many of you understood what I explained? Right, okay. Quickly, this is an additional note. If you need, you can write down this one as well. But somehow write down this one. It's very important. Quickly. So when you finish writing, please raise your hands. Then I don't know. And also now, there's a plan like this now. Because now, next week onwards, now we are doing this online classes. Through there's an online platform called Ace Academy. So I thought of join with them and I thought of continue all these online classes, 24 online class and 25 online class. Right. So next month onwards, you need to do all your payments through that platform. Right. You don't directly pay to me. So you want to pay for them. Then you want to what? So I will send all the guidance in a PDF. Then you can understand. So then, if someone need to purchase recordings, then you can purchase all the recordings through going to that platform, and you can buy it or purchase it. Or, so it will be very convenient rather than because now, even though I do this online class, sometimes some people they need recording, sometimes they could not join for one day. Then it's really difficult to handle all these things. So I thought of join with them. Then it will be very well organized online class as well as so more students can reach to that platform. So by thinking about them, I thought of do these online classes hereafter through this online. Nothing different, but basically what you do, you are enrolling through that platform. That's the only difference. Then much advantage for you people is if you need to purchase recordings of all previous lessons, you guys can purchase because all the recordings are available in their cloud. That's the difference. Okay, right. I will let you know the details as a PDF. I will send today or if not this week. Next week onwards, you are going because everyone must need to open account in Ace Academy, that website. When you just type Ace Academy, then there will be a website pop up. So you want to create an account like FB account, Google account. Just create an Ace Academy account. So don't worry, I will send all the guidelines through that PDF. Okay. If you finish copying, raise your hands. If you finish copying, raise your hands. Okay. Quickly. So I'm erasing these two diagrams, right? I'm erasing. Right. And also after you finish drawing this diagram and draw this diagram also with me, then I'll explain. Okay. So always keep your attention and draw this diagram with me. for this diagram as well. Don't waste your time. So I think you guys finished drawing this diagram as well. I'll erase it. Okay. So draw the diagram with me. Then when this spring now, you can clearly see that uh, simple M mass is connected to a horizontal spring. Now this first diagram shows that when the spring is under natural length, if your spring is at natural length, that means your spring is not stretched or compressed. That's why we call spring is under natural length. Then when your spring is under natural length, we say that this point as center point, if not equilibrium point, if not center of oscillation. As this point is point capital O. This point capital O we are calling equilibrium point, if not center of oscillation. So write down with me equilibrium point, if not point of oscillation. Point of oscillation. Right. Right. Okay. Then here what happened? Let's say mass this object is simple limb. This object's mass is simple limb. Simple limb. Right. Right. So here is your point capital O. This point capital O. I say this point is point capital A. And I will say this point is point capital A. And I will say this point is point capital B. Very carefully listen what I'm explaining. Right, okay. Right? Okay. Okay. Now look at it. Now, very carefully listen. Now, an object of mass simple limb is connected to a spring. I explained that this figure, this spring is under its natural length. Next, what I do, I am stretching the spring. So by providing a force on this object, I'm stretching the string up to this position. When this object reach point capital A, what I do? When this object reached at point capital A, I release this object from rest. Very carefully listen. Right? I'm stretching the spring up to this position. Right? When this object simple limb reach at point capital A, I release from rest. Then we know that anyone can understand when I release this object, what is the direction of motion of this object? When I release this object, what is the direction of motion of this object? Left side direction. Anyone can understand. So this object moves from rest. This object moves to the left side direction from rest 0 ms minus 1. I'll ask that what is the direction of force acting on this object? Tension force on the object, what direction? Leave a reply everyone. When I release this object from rest at point capital A, what is the direction of tension force acting on the object? Leave a reply everyone. Direction of tension force acting on the object. Leave a reply everyone. What is the direction of tension force acting on the object? What is the direction of tension force acting on the object? Left side direction. Left side direction. So tension force acting on the object is left side direction capital T. You understand? When you consider this object, when this object is released from rest at point capital A, tension force acting on the object is left side direction. And then we know that because of this tension force, object accelerates to the left side direction. Because of this tension force, this object is accelerating in the left side direction. I say acceleration is simply because of the tension force, this object is accelerating. Right? Right. All of you understood up to here. Okay. All of you understood. Let's say acceleration is okay. Okay. This object is accelerating to the left side direction. We know that. Now I'm going to consider, very carefully listen. I'm going to consider a general position. A general position of this object. Now we know this object moves to the left side direction. When this object has reached somewhere here, look at it. When this object has reached somewhere here, we know object is accelerating. When this object has reached somewhere here, direction of acceleration will be simple A. The displacement to the position of this object from the equilibrium point. The displacement to the position of this object from the equilibrium point. If I mark that, that is simple x. Simple x, right? Simple x. Okay. Then you can clearly understand, look at it. When this object is at this position, direction of acceleration is to the equilibrium point. Direction of acceleration is toward the equilibrium point. Displacement is a vector. Direction of displacement is in opposite direction, right? Now basically what happens? This object moves to the left side direction and reaches equilibrium point. And then what will happen? This object passes the equilibrium point. When the moment this object passes equilibrium point, you can understand this spring start to compress, right? Right? From capital A to capital O, spring was under what? Extension. Right? As this object moves to the left side direction, when the moment this object reaches equilibrium point, there is no tension force on the spring. Why? When this object is at equilibrium point, again, spring is at the natural length. So therefore, there is no tension force acting on the spring. As soon as what happens? As soon as your object passes equilibrium point, again your spring starts to compress. Your spring starts to compress. I'll ask that at this position, what is the direction of tension force? Now we know that when you consider in between capital A and capital O, direction of tension force on the object is left side direction, right? Why? Extension was there. Now I'll ask that when this object passes equilibrium point and moving further to the left side direction, we realized this spring is compressed. The spring is getting more and more and more compressed. Then I'm asking, then what is the direction of tension force on the object? That is in the right side direction, right? That is the right side direction. That is in the right side direction. You guys can understand. So I mark like this. Okay, tension force in right side direction, capital T, right? Then we know that always direction of acceleration is in the direction of force, right? When you consider the simple in mass, what is the direction of force? Tension force, left side direction. Then always direction of acceleration is in the direction of resultant force. The tension force is at the left side direction, therefore acceleration was at the left side direction. Now we want to understand between point capital O to capital B in that region, when your spring is getting more and more compressed, direction of tension force on the object is right side direction. Therefore, understand direction of acceleration is in right side direction. I think all of you understood up to here. Raise your hands. Up to now, everything is very clear. Raise your hands. Up to now, everything is very clear. Up to now, everything is very clear. Raise your hands. Then if I measure the displacement from this equilibrium point, if I measure the displacement to point capital B, that is simple x. But here you want to understand direction of acceleration towards the equilibrium point, but direction of displacement is in this time opposite to acceleration direction, right? How many of you finished drawing this entire diagram? Raise your hands. Raise your hands. How many of you finished drawing this entire diagram? I think all of you finished, right? Then write down characteristics of simple harmonic motion. Characteristics of simple harmonic motion. Today, I don't know, we can do questions. I'm not sure. Today, we are learning this simple harmonic motion. Characteristics of simple harmonic motion. Number one, all the simple harmonic motion are periodic motion. First one, all the simple harmonic motions are periodic motion. Right? Number two. Now we know that now. Now all of you know what is periodic motion. Now look at here. In simple harmonic motion also, basically what happens? Just consider this example. Motion of an object connected to a horizontal spring. This object is also what's happening. This object is also keep on moving, repeating same motion again and again. This object will move this way, this way, this way, continuously going back and forth. So therefore, this object repeats the same motion. Therefore, understand all the simple harmonic motions are periodic motions, right? But you don't think about an opposite way. All the simple harmonic motions are periodic motions, but you want to understand all the periodic motions are not simple harmonic motion. You understand? All the simple harmonic motions are periodic motions, but all the periodic motions are not simple harmonic motion, right? Okay. Inside the bracket, write down like important. Inside the bracket, important. Red color pen. All the periodic motions are all the periodic motions are not simple harmonic motions. All the periodic motions are not simple harmonic motions. All the periodic motions are not simple harmonic motions. Second characteristic, number two, acceleration inside the bracket or force, close the bracket. Acceleration inside the bracket or force of the moving body is directly proportional to the is directly proportional to the displacement from equilibrium position. Displacement from equilibrium position. I explained right. Acceleration is always directly proportional to displacement from equilibrium point. You can understand. Third characteristic, acceleration inside the bracket or force close the bracket. Acceleration inside the bracket or force close the bracket is always directed towards, is always directed towards the equilibrium position. The equilibrium position. Right, I think all of you understood me. No matter object at any position, very carefully understand, while object moves in a simple harmonic motion, any position in the motion, always acceleration directed towards the equilibrium point. No matter in the motion, where is your object? Any position in the motion, direction of acceleration always towards the equilibrium point. And also that acceleration value is directly proportional to displacement. Then we call that type of motion as simple harmonic motion. I think I explained me everything in proper way. Okay, right. Now topic building characteristic equation. Topic building characteristic equation for simple harmonic motion. For simple harmonic motion. For simple harmonic motion. Now write down a note. In a simple harmonic motion, comma, in a simple harmonic motion, comma, the acceleration acting on the object, the acceleration acting on the object is directly proportional to the displacement, is directly proportional to the displacement. Okay, now draw this diagram. Uh, now draw this diagram. Now we are going to derive the characteristic equation of simple harmonic motion, right? Characteristic equation of simple harmonic motion. Let's say now, if this is your object, moves in a simple harmonic motion, okay? Let's say mass of this object is simple m, simple m. Let's consider this is your equilibrium point, if not center of oscillation of the simple harmonic motion. Equilibrium point, if not center of oscillation. Now, when you consider general position of this object in a simple harmonic motion, this object moves in a simple harmonic motion in this direction. When you consider general position in simple harmonic motion, let's say displacement is simple x. Displacement to this position is simple x. Displacement measured from equilibrium point. Simple x, right? Then acceleration, always acting to the center. Acceleration to the center. Acceleration, simple a. And then we know that always acceleration is directly proportional to displacement. always this acceleration is directly proportional to displacement, right? We usually, in order to remove this proportionality, we are using a constant. Acceleration what? Equals a constant, right? A constant that is k. A constant that is k. That constant k, then simple x. Then simple x. But we are using a negative sign here. A equals minus kx. A equals minus kx, right? Later on, they found that this constant is equals to square of angular velocity. A equals minus angular velocity omega square, simple x. Then you might have a problem. Now you guys might have understood acceleration directly proportional displacement. In order to remove this proportionality, we are using equal symbol and a constant k. Now you told something about negative sign. Sometimes you are not very clear about this negative sign. Now, do you know why we are using this negative sign? The reason is, look at the relationship between acceleration and displacement. Any instant in the motion, object's acceleration direction and object's displacement direction opposite to each other. In this diagram, look at here. Direction of acceleration is left side direction. Direction of displacement is in right side direction. Then you can clearly understand acceleration direction and displacement direction are opposite. Why we are using this negative sign? To represent that opposite relationship between acceleration and displacement. Why we are using negative sign? To represent the relationship between that opposite relationship between acceleration and displacement. That's why we are using this negative. But when you do questions, you don't need to bother with this minus symbol. You can take a equals kx. Next problem that you have is, I understood k is a constant, but your problem is, instead of k, why you substituted omega squared? Now you won't understand. Later on, you will understand. K equals omega squared. Okay, k is a constant. K is a constant. I don't explain right now why k equals angular velocity squared. I will explain later. Now, temporarily write down k is a constant. Constant. Right. Now, what is this omega? This is the characteristic equation of simple harmonic motion. The characteristic equation of simple harmonic motion is A equals minus kx. If not, A equals minus omega squared. The characteristic equation of simple harmonic motion. Finish writing. Now we'll mark this omega. Omega means what? Put down omega hyphen. Write down angular velocity of an object. Angular velocity of an object in a circular motion. Angular velocity of an object in a circular motion corresponding to simple harmonic motion. Corresponding to simple harmonic motion. What is omega? Angular velocity of an object in a circular motion corresponding to simple harmonic motion. I will explain why we call angular velocity. I will explain later. No need. If you understood these two equations, that's fine. Okay. Now red color pen. Important. Red color pen important. Red color pen important. The physical meaning of negative sign in the equation is, the physical meaning of negative sign in the equation is Always the direction of displacement. Always the direction of displacement. Of the object is opposite to the direction of acceleration. I explained, right? Opposite to the direction of acceleration. Right? Right? Okay. Therefore, now separately write next point, separately write down. Therefore, the characteristic equation. Therefore, the characteristic equation for simple harmonic motion. For simple harmonic motion can be represented as below. Can be represented as below. Can be represented as below. Right? Now, suppose if an object moves in a simple harmonic motion, let's take about spring and set of spring setup. This object mass is, let's say, simple M. Equilibrium point is point capital O. Tension capital T. Tension force on this object is capital T. The tension force on this object is capital T. At this instant, acceleration is simple A. That direction is same direction of force. So then, let's say displacement is simple X. Equilibrium point is point capital O. Displacement is, let's say, simple X. Displacement simple X. Now we know that in mechanics we learned that spring constant, tension force in a spring. You know Hooke's law, right? F equals kx equation we learned. F equals kx equation we learned, right? So therefore, let's say capital here simple K. Here K means what? Here K means spring constant. Okay, here K means what? Spring constant. Now you know here K means spring constant. Spring constant. Right now we know characteristic equation. Suppose if this object moves in a simple harmonic motion, we know characteristic equation is what? A equals minus omega squared x equation, right? Now what I am do now, at this instant, there is only one horizontal force acting on this object, capital T tension force. Because of this tension force, at this instant, very carefully understand why I am using instant. At this instant, tension force is capital T. At this instant, acceleration is simple A. So then what can I do? Towards the equilibrium point, I can apply F equals mb. Applying F equals mb towards equilibrium point. Towards equilibrium point. Towards equilibrium point. Right. Applying F equals mb towards equilibrium point. Then what is my force? In horizontal direction, there is only one force. Tension force, left side direction, capital T. So capital T equals mass is simple m, acceleration simple a in that direction. So I applied F equals ma this direction towards equilibrium point. I applied F equals ma left side direction. Tension force also in left side direction. Acceleration is also in left side direction. Okay. Now you know that you guys might have learned in mechanics, F equals Kx equation. Raise your hands, how many of you know F equals Kx equation? When the spring stretches, if you want to find the tension in the spring, we are using F equals Kx equation. It's a normal thing, right? You guys might have learned those things. I don't explain them. Then I can see this tension force equals what? This tension force equals what? Tension force equals what? If I apply F equals Kx that equation, I can say tension force equals K means what? Spring constant. Okay, here K means spring constant. K means spring constant. Now look at it, very carefully listen. When I apply that, if I want to find this tension force, we know in mechanics we learned that F equals Kx equation. Then in that equation, F means tension force capital T, K means spring constant, X means displacement, if not extension. Tension force is in left side direction, right? Tension force in left side direction. But displacement is also a vector. Displacement is in right side direction. If I consider now, I applied F equals ma also to the left side direction. So tension force in left side direction, but your displacement is in right side direction. So therefore, what we do, we are using minus x. You understand why we are using minus x? Tension is in left side direction, displacement is in right side direction. Therefore, we are using minus to mention the opposite relationship. This will be my equation 2. Equation 2. Equation 2. Then I can say from equation 1 and 2, I can say, from equation 1 and 2, I can say, look at it, 1 and 2, I can say that the tension relation equal. Therefore, I can say K minus X. I can say here K means spring constant, don't misunderstand. K minus X equals what? ME. ME. Right? So when I subject simple A equals minus K over simple M, K over simple M, simple X. Raise your hands. Up to now, everything is very clear. I hope that all of you can understand up to now, right? Everything is very clear, right? Now, here K means spring constant. Look at here, K means spring constant. Now, you know that for this given spring constant is a constant, mass of this object is a constant. Then acceleration equals minus a constant simple x. Do you understand? So I can write down this constant as what? Omega squared. Because A equals the acceleration equals minus omega squared x. Right? Then what is this K over M? K over M equals omega squared. So this K over M equals, understand, minus omega squared. Because why? A x minus, then who acts as omega squared? This K over M. Therefore, I can say this object is moving a simple harmonic motion. What's my omega value? Omega equals, very important thing is, omega squared equals what? K over M. More important thing is, omega squared equals what? K over M. Therefore, angular velocity can be written as what? Spring constant over mass of the spring whole root. This is an important equation. For a spring, it's an important equation. Generally, hands up, how many of you understood how I came to this conclusion? Raise your hands, how many of you understood how I came to this conclusion? Raise your hands, how many of you understood this idea? Right, okay. Now quickly copy down this one. Copy down. Now some people misunderstand with this K, right? Understand this K means a constant. It's not spring constant. So it's a normal constant. But here this K means spring constant. right? So don't you think about this k and this k both are same, wrong. Okay, this is something different constant. It's omega squared. This is spring constant. Don't you misunderstand with that. Quickly, right on them. So raise your hands. How many of you finished writing? Quickly. Now we'll do a sample question, SQ1. We'll write a sample question, SQ1. An object of 5 kilogram mass. An object of 5 kilogram mass moving in a simple harmonic motion. So SHM, you just write short term SHM, moving in a simple harmonic motion. Full stop. If spring constant K equals, if spring constant K equals 50 Newton per meter, 50 Newton per meter, comma, what is the acceleration of the object? What is the acceleration of the object? When the extension of the spring is, when the extension of the spring is 20 centimeter. When the extension of the spring is 20 centimeter. So maximum I will give 3 minutes. If you finish getting the answer, put the answer in the chat box quickly. Start doing this question, very basic substitution. It's not a difficult question. Start doing that question quickly. How many of you got the answers? If you got the answers, put the answer in the chat box quickly. If you got the answers, put the answers in the chat box quickly. Everyone. Quickly. Yes, time is enough. It's a base substitution, right? Because we know that now, if that object is moving in a simple harmonic motion, we know it follows characteristic equation A equals minus omega squared x. So then A equals SQ1, A equals minus omega squared x. Then just now we wrote that if it is a spring, omega means what? Omega squared means spring constant over mass. So when you do questions, you don't need to apply this negative sign. It's not compulsory. Then omega means what? Omega squared means spring constant over mass k over m. Simple x. Now you have to find simple a. They have given spring constant is how much? 50. I think they have given spring constant is 50. Mass is 5 kilogram and extension, that means simple x, that is 20 centimeters. 50, 5, mass, extension 20 centimeters. How do you convert to meters? 20 into minus 2, 10 to the power minus 2. If you want to convert centimeters into meters. Then 5 cancel out here, it's 10. 10 into 20 means 200. 200 to the power minus 2 means how much? Just 2 ms minus 2. Acceleration is just 2 ms minus 2. It's a base substitution. Summary, red color pen. Summary, red color pen summary. If any motion that happens in the universe, if any motion that happens in the universe, red color pen, can be represented in a way of, can be represented in a way of A equals minus kx, A equals minus kx, or A equals minus omega squared x, A equals minus omega squared x, comma, no matter what kind of motion it is, no matter what kind of motion it is, comma, it's a simple harmonic motion. It's a simple harmonic motion. It's a simple harmonic motion. Right, okay. Now raise your hands. Up to now, everything is very clear. How many of you understood everything up to now very clear? Raise your hands. So tute will be sent in this week, okay? So not yet printed. It will be sent in this week, okay? Right, okay. Now we'll take a break. Okay, now time is exactly 8:25. Come at 8:35. Then we are starting about amplitude, frequency. Come at exactly 8:35. We'll take a break. Right. Okay. Right. Okay. Now your topic: amplitude of an object in simple harmonic motion. Your main topic: amplitude of an object in simple harmonic motion. Quickly. Then write down the maximum displacement in one direction. Now you want to understand what is this amplitude? Amplitude means what? The maximum displacement in one direction from the equilibrium point. From the equilibrium point. From the equilibrium point is defined as amplitude. Is defined as amplitude. Now look at it. Very carefully listen. Right, okay. Now when an object moves in a simple harmonic motion, right? Look at it. Now we say this point is our equilibrium point, capital low. Equilibrium point, capital low. Equilibrium point, capital low. Equilibrium point. Now an object moves in a simple harmonic motion. When you consider motion of simple harmonic motion, the maximum displacement obtained by the object from equilibrium point, very carefully listen. When this object moves in a simple harmonic motion, the maximum displacement obtained from the equilibrium point in one particular direction, right? That's we call as amplitude, right? So this object is moving in between, let's say this object is moving in between here to here. This object is moving in between this point and this point. So from the equilibrium point, the maximum in, right, when this object is exactly at this point, capital A, object is at the maximum displacement in one direction from the center. If not, when this object is exactly at this point, capital B, object is at the maximum displacement from point capital O, right? So in between these regions, when your object is at this portion, no, when your object is somewhere here, displacement of the object is not maximum, right? When object is at point capital A and capital B, object is at the maximum displacement. We are calling that maximum displacement as what? Amplitude. If it is in right side direction, we say it is positive amplitude. When the displacement is to the left side direction from the equilibrium point, we say it's negative amplitude. So I think you guys understand, right? Okay, then I can mark something like this. This is positive amplitude, this displacement, plus capital A. This is negative amplitude. It's negative amplitude. This is what? Minus capital A. Amplitude is a distance, right? Okay. Now, okay, draw this diagram. This diagram. Quickly, draw it. Now, normally understand in generally, when the object is at the amplitude, it can be positive amplitude. If not, it can be negative amplitude. When the object is at the amplitude, understand velocity is zero. Do you understand? When this object is moving in a simple harmonic motion, when the object is at the amplitude, it can be at the positive amplitude. If not, it can be at the negative amplitude. Velocity is zero. Velocity is zero. It's a very important point, right? You must remember, when this object is at the amplitude, velocity is zero. When the object is at the equilibrium point, velocity is maximum. So throughout the motion, understand velocity is changing. For an example, let's say this object is moving this direction. Exactly at the amplitude, velocity is zero. When this object is moving towards left side direction, until equilibrium point, velocity of this object is increasing. Velocity is increasing. Exactly at the equilibrium point, velocity will become maximum. Exactly at the equilibrium point, velocity of this object will become maximum. Velocity will become maximum. Then still your object further move into the left side direction. But now from equilibrium point to capital B, now velocity is decreasing. Velocity is decreasing. Exactly at point capital B, velocity becomes zero. Suddenly change the direction. Now this direction again, velocities keep on increasing. Velocity is increasing. Exactly the equilibrium point, velocity is maximum. Beyond that point O, velocity start decrease. Velocity is decreasing. Exactly point A, velocity will become zero. Right? I think you guys understand. Now draw that one as well. Yes. Then I'll ask a question. Now we know that acceleration equals A equals minus kx. Now raise your hands. How many of you say that now? Throughout the simple harmonic motion, velocity varies, obviously, because object is accelerating. Throughout the simple harmonic motion, you want to understand velocity varies. Magnitude, direction varies. Raise your hands. How many of you say that in a simple harmonic motion, throughout the motion, acceleration remains constant? Raise your hands. How many of you say that throughout the simple harmonic motion, acceleration remains constant? How many of you say that acceleration also varies? How many of you say that acceleration also varies? Yes, acceleration also varies, right? Because not only magnitude but also direction also varies. From capital A to capital O, what is the direction of acceleration? Velocity is increasing in this direction. So direction of acceleration is in that direction. Acceleration. Then I mentioned that from point capital O to capital B, when this object is moving to the left side direction, when this object is moving to the left side direction from capital O to capital B, velocity is decreasing. This direction deceleration, velocity is decreasing from O to B. This direction deceleration means acceleration is in this direction, right? Acceleration. I told you also acceleration is what? Equals to minus kx. When displacement changes, because when object is at different locations in the motion, x changes. When x changes, we know acceleration changes. So therefore, this simple harmonic motion is not like linear motion. In linear motion, throughout the motion, acceleration is constant. But in simple harmonic motion, depends on every instant, the next instant the motion, every next instant the motion, acceleration changes. Not only magnitude, but also direction also changing. So now you must have a rough understanding. I will give us a note at the end, but you must have a rough understanding. Okay, is okay. So then that is also done. Then write down what is the unit of amplitude. Write down a point. Unit of amplitude meters. I forgot to mention the notation of amplitude in that topic. Inside the bracket, write down notation of amplitude is capital A. Notation of amplitude is capital A. Then write down unit of amplitude meters. Dimensions of amplitude capital L. Dimensions of amplitude capital L. right? Now next topic, frequency of an object in SHM, right? Next topic, frequency of an object in SHM. Notation simple if. Notation simple if. Write down. Now in circular motions as well as in rotational motion, as I explain what is frequency. Frequency means what? A frequency means, now in circular motion, number of circular motions per unit time. If not number of circular motions per 1 second, we call as frequency, right? But in oscillations, what is frequency? Number of oscillations per unit time is we call as frequency. That means every 1 second, how many oscillations happening? How many times object is repeating the motion? Every 1 second, what is the number of oscillations? That's what we call as frequency. So write down under frequency of an object in SHM, write down number of oscillations in 1 second. Number of oscillations in 1 second. Number of oscillations in 1 second done by the object. Done by the object in SHM. In SHM. Right. Then you know that. What is the unit of frequency? Leave a reply. What is the unit of frequency? Leave a reply. Hertz, right? Hertz. H is it hertz, if not per second. So you can write down units of frequency as hertz, if not per second. Then dimensions of frequency, capital T minus 1. Dimensions of frequency, capital T minus 1. Quickly. Right? Then subtopic, time period of an object in SHM. Subtopic, time period of an object in SHM. Inside the bracket, capital T notation. Right? Now frequency means what? How many number of oscillations occurred in 1 second? Then what is this time period? How long? If not, what is the time taken by an object to have one complete oscillation? Frequency means within 1 second, how many number of oscillations? Time period means for one oscillation, what is the time taken? Write down. Time taken for one complete oscillation. Write down. Time taken for one complete oscillation. Time taken for one complete oscillation is defined as time period. Is defined as time period. The units of time period, seconds. Dimensions of time period, capital T. Then write down next point. Units of time period, seconds. Dimensions of time period, capital T. Okay. Right. Then subtopic, relationship between time period and frequency. Relationship between time period and frequency. Quickly. Topic, relationship between time period and frequency. Okay, right. Write down something like this. Now, when you're writing, understand, write down. That's very important. Okay, when you're writing something, understand, write down. Write down. If an oscillation, if an oscillation frequency of an object is simple if. Now you know what is simple if. Simple if means what? Number of oscillations within 1 second. Okay, write down. If an oscillation frequency of an object is simple if, then comma, next line, time taken for simple if number of oscillations equal. Next line, time taken for simple if number of oscillations equal. How much? Put a reply. How much? Time taken for simple if number of oscillations equal how much? Put a reply. Leave a reply. No one replied yet. How much? Yes, 1 second. 1 second. It's 1 second. Because if means what? Number of oscillations is 1 second. In order to work a simple if number of oscillations, time taken is 1 second. Equals 1 second. Equals 1 second. Next line. Next line. Next line. Time taken for one oscillation. Time taken for one oscillation. How much? Time taken for one oscillation equals how much? Now, time taken for simple if number of oscillation is 1 second. Then if you want to find the time taken for one oscillation, if you want to find the time taken for one oscillation, that means time period. Simple if number of oscillations occurred in 1 second. If you want to find one oscillation, what is the time? What you going to do? F over 1 over t equals what? 1 over f. Time taken for one because it's a common sense, right? F number of oscillations occurs in 1 second, then one oscillation occurs in 1 over f seconds equal 1 over f equal 1 over f. Therefore, we can say what? Capital T equals, highlight, capital T equals 1 over f. Highlight this one. This is an important equation learned by heart. You want to remember this equation. Raise your hands. How many of you understood up to here? Everything is very clear? Raise your hands after everything is very clear. How many of you understood up to now? All right. Then next topic, relationship between frequency and angular velocity. Next topic, relationship between frequency and angular velocity. Relationship between frequency and angular velocity. Now that's very easy, right? I think you guys know that. You know time period equals to phi omega, right? Circular motion. Circular motion, right? Now we know that time period capital T equals what? Circular motion we learned 2 phi over omega. Equation 1. And now we know that time period equal. Now what's the goal? Time relationship between frequency and angular velocity. Now we learned that time period equals what? 1 over simple if. Equation 2. Then I can say from equation 1 and 2 I can say what? From equation 1 and 2 I can say what? I can say 1 over f equals 2 phi over omega. So therefore, F equals what? F equals omega over 2 phi. This one also highlight it. Copy down quickly. It's not difficult. Now this next topic is very important topic. Now this topic is very important topic. It's very important. So if I could explain this chapter, this section, then we can do plenty of questions actually. It's very important thing. So therefore now very careful listen. Put your main topic. The instantaneous velocity of an object in simple harmonic motion. Your topic, instantaneous velocity of an object in simple harmonic motion. Very important topic. Instantaneous velocity. Now by the name it suggests instantaneous velocity at a particular instant velocity. That's what we call as instantaneous velocity. Instantaneous velocity of an object in SHM. Your topic. Now again we will draw the springs. Draw this diagram with me. Draw these diagrams. Now that's a spring. Now initially that spring is a natural length. Draw this diagram, okay? Now initially that spring is under its natural length. Right? Now an object of mass simple limb is connected to this spring. Okay. Simple limb mass. This is our equilibrium point capital low. Equilibrium point capital low. Then what we do, as discussed previous time, what we do, I stretch the spring until a location somewhere here. Then I release the object from rest. Next diagram. Okay. Mass simple limb, my object. Now I'll ask a question. Now I have released, very carefully listen, I release this object, I stretch the spring, I release this object from rest. I'm asking, from this equilibrium point, the displacement to this object. What is the displacement to this object from the equilibrium point? Give reply. If this object has stretched and if this object is released from rest, I'm asking, what is the displacement from this object to the equilibrium point? Leave reply. That is what? That is amplitude. That is the amplitude. I think you guys understand me. Or always understand because we learned that velocity is zero only in amplitudes. Exactly at the equilibrium point, velocity is maximum. So always understand that important thing. Velocity is zero in amplitudes. Velocity is maximum at the equilibrium point. So when you release an object from rest means this object is at its amplitude. Capital E. Amplitude is capital E. Maximum displacement is capital E. Amplitude capital E. Capital E. Right? Right. When t equals 0, I release this object. When t equals 0, I release this object. Then let's say after simple t time later, this object has come a position somewhere here. After simple t time later, this object has come a position somewhere here. If I draw that diagram, if I draw that diagram, a position somewhere here. Then the displacement. I say when t equals simple t, when t equals simple t, at this position, displacement of this object from the equilibrium point, I will say simple x. Displacement is simple x. Displacement is simple x. Right now, this object is moving towards equilibrium point. Therefore, at this instant, this object is having a velocity, right? I say velocity of this object at this instant is capital V. Velocity of this object at this instant is capital V. Capital V. Now, what's my goal now in the topic? What is the topic? What we want to find actually? We want to find instantaneous velocity at a particular instant. Object moves in a simple harmonic motion. When t equals 0, I know velocity of this object is 0. When t equals simple t, at this instant, I want to find this object velocity. So I'm going to derive an equation for instantaneous velocity. Now, how I'm going to derive this equation? I'm going to apply conservation of mechanical energy. I'm going to apply conservation of mechanical energy for this portion of the system and this portion of the system. Very careful listen. I say this portion is capital A portion. This portion is capital B portion. Considering capital A and capital B of the system, I am going to apply conservation of mechanical energy. Why? Why I am applying conservation of mechanical energy? To get an equation for instantaneous velocity capital V. So I am applying applying conservation of mechanical energy. Applying, look at here very carefully, conservation of, now you write down nicely, conservation of mechanical energy, conservation of mechanical energy for capital A portion and capital B portion. For capital A portion and capital B portion. Right? Okay. Now this time your system is, very carefully listen, your system. Your system includes two objects. One is spring, other one is object. Your system is having two things. One is spring, other one is object. When the system is at position A, what is total energy? Now we can assume potential energy is 0 because we can assume the system is on the ground. If you consider this level as your 0 potential level, we can say that there is no potential energy for the system. But we can understand when your system is at position A, velocity of the object is 0, velocity of the spring is also 0. So therefore there is no kinetic energy. There is no kinetic energy. So kinetic energy at A is 0. Kinetic energy at position A plus this is 0. But please tell me, someone leave a reply. When you consider your system, there is no kinetic energy. Why? Object is also at rest, spring is also at rest, there is no kinetic energy. I'm asking, what is the other form of energy in this system at position A? Leave reply. What is the other form of energy in the system at position A? Leave reply. Leave reply. So I'm expecting replies from everyone. Be humble to leave a reply. That is elastic potential energy of the spring, right? Elastic potential of the spring. Elastic, when you're writing, nicely write down now. Elastic potential energy. Energy at position A. Then total energy means what? There is no kinetic energy or gravitational potential energy, but spring is stretched. Spring is stretched. Therefore, what? Spring is having elastic potential energy. So therefore, total energy at position A is only the elastic potential energy of the spring. This must be equal to what? According to conservation of mechanical energy, total mechanical energy of the system at position B. So when your system is at position B, this object is having kinetic energy because this object is having a velocity. So therefore, this object is having kinetic energy. Spring is also still stretched. Therefore, spring is having potential energy. So therefore, kinetic energy at position B plus elastic potential energy. Elastic is elastic potential energy, okay? Elastic potential energy at B. Elastic potential energy at B. Now we know kinetic energy at A is 0. What is the equation we learned for elastic potential energy in mechanics? There are two equations we learned. One equation is elastic potential energy means what? We learned that half Fx tension on the spring extension x. That is one equation. But most popular equation is what? Elastic potential energy equals half spring constant k x squared, half k x squared. This is the most popular equation, half k x squared. Then I can find at position A extension, simple x is capital A, right? Extension is capital A. Then I can say that half spring constant of the spring is k, extension is what? Capital A square. That must be equal to what? Kinetic energy at B. Mass of this object is simple m, half. What is the equation for kinetic energy? Half mv squared. Equation for kinetic energy is what? Half mv squared. You must know these things, right? Then half, mass is simple m, velocity is capital V. That's what I want to find. We are going to find instantaneous velocity. Half m v squared plus elastic potential energy of the spring at this position B. Extension is simple x, half k x squared. So I can cut all the half terms, right? Then I will obtain something like this. If I cut all the what? X half terms, look at here, then I will obtain, I will bring this one here. Then I will obtain, look at it, Ka squared equals mv squared plus again kx squared. If I subject mv squared, you will understand mv squared equals what? Mv squared equals Ka squared minus kx squared. If I take k as my common factor, I will obtain a squared minus x squared. If I study m v squared, if I subject v squared, I will obtain what? Look at it very carefully. Listen. K over simple lim a squared minus x squared. Look at here. I am getting k over simple lim. I am getting here k over simple lim. K over simple limb. Now someone leave a reply. What is K over simple limb? This K over simple limb means what? Can you remember? That is omega squared. This is your omega squared, right? Omega squared, V equals what? Omega squared. Not omega. K over simple limb means omega squared, right? Not omega, it's omega squared. V squared equals A squared minus X squared. Now some people cut these square terms, but we can't cut these square terms. Why? The reason is there is minus. Therefore, we can't cut all these square terms. Okay. This is the important equation. Super highlight this equation. Very, very important equation. This equation gives what? Instantaneous velocity. Look at here. Look at here. This equation gives instantaneous velocity in terms of omega, A and X. Raise your hands. How many of you really understood the derivation and understood this derivation? Raise your hands. How many of you really understood the derivation? Raise your hands. Keep on raise your hands. Wait. How many of you understood? Most of you understood. Then that's fine. Copy down. When you finish copying, raise your hands. When you finish copying this one nicely, raise your hands. Yeah, it's a standard equation. You can directly apply. So you learn by heart that equation directly. V squared equals omega squared, A squared minus X squared. That's a standard equation. If you finished writing, raise your hands. If you finished writing, raise your hands. I think time is enough, right? Right, okay. I think you guys understood up to here. Everything is, I think, very clear. So please don't make anything not clear, because in case if you have plenty of confusions, then you are not able to understand coming things. Right. Okay. Right. Right. Now you understood that equation. Right. But if you need, but generally we are using no. Okay. Now normally we are using always. You want to remember that this v squared equals omega squared a squared minus x squared. But we can subject v actually. But normally we don't use that equation. Use more every equation you are using every time you are using this equation. Right, but when you subject v, you will get what? When you subject v, if you take root in both sides, v equals omega root a square minus x square, right? So write down this equation as well, but mostly we are using this equation, right? Then write down something like this. Write down, write down. Let's consider a mass connected to a horizontal spring. Let's consider a mass connected to a horizontal spring. The mass attached to the spring is displaced. The mass attached to the spring is displaced. The mass attached to the spring is displaced a distance capital A from a distance capital A from center and released from rest. Center and released from rest. Okay. Now subtopic. Now you want to understand now this equation v squared equals capital A squared, sorry, v squared equals omega squared capital A squared minus x squared. We use that equation if you want to find instantaneous velocity. Suppose if you know the amplitude, if you know displacement and angular velocity, if you want to find at a particular instant velocity of the object, we are using that equation, right? Now, now I explained that in a simple harmonic motion, I explained velocity varies, right? When object moves in a simple harmonic motion, different instants, object's velocity is different. Then you know, currently you know that velocity is zero at the amplitudes. Without thinking twice, you can say that suppose if your object is at the amplitude, we know velocity is zero, right? And also we know that velocity is maximum at the equilibrium point. I explained. When object moves in a simple harmonic motion, I explained that velocity is maximum at the equilibrium point, velocity is zero at the amplitudes, because you can clarify it. When object is at the amplitude, you can say what? When object is at the amplitude, we can say what? What is your x value? When object is at the amplitude, your x value is capital A. Then here a squared minus capital A squared, 0, we will become 0. Now the topic is what now? I ask you to put the topic maximum velocity of an object in a stretching. Now your topic is maximum velocity of an object in a stretching. Now we know velocity is maximum at the equilibrium point. I am going to derive an equation for maximum velocity. How do I do that? How do I derive an equation for maximum velocity? Right? Okay, look at it. Now we know that this is the general equation. This equation can be applied for any instant. Now we know instantaneous velocity equals what? At any instant, even your object is at the amplitude, even your object is at the equilibrium point too. In between them, Any instant you can apply this equation, v squared equals omega squared capital A squared minus x squared. Now what's my goal? I want to find the maximum velocity. But we know velocity is maximum at the equilibrium point. Velocity is maximum at the equilibrium point. Look at it. Now what will happen? Now here omega is a constant. In that particular SHM, amplitude is a constant. What would happen when x changes? We know that when x increases, what will happen? We know when x increases, when x is increasing, a squared, when x is increasing, x squared increasing, when a squared minus x squared, what? When x increases, what will happen for a squared minus x squared term? Decreasing. Then what will happen? Velocity is decreasing, right? Am I correct? When your x is increasing, a squared minus x squared term is decreasing, therefore velocity is decreasing. So therefore you want to understand when x increases, velocity decreases. When x decreases, displacement decreases, your velocity is increasing. If you want to find the velocity, maximum velocity, velocity will be maximum when your displacement is minimum, right? When your x is minimum, v is maximum. Am I correct? When x is minimum, we can say what? When x is minimum, velocity is maximum. V is maximum. You guys understand? Then what is the minimum x? Minimum displacement is 0. Then we can say what is the minimum x? The minimum x is what? 0. Right? We know velocity is maximum when x is minimum. Minimum x value is 0. Then what is your Vmax? Then what is your Vmax? You can find your Vmax by how? Then you can say Vmax squared equals omega squared a squared minus, now x is minimum, 0. 0. Therefore we can say V max squared equals omega squared capital A squared. If you take root in both sides, we can write down an equation for maximum velocity as what? A omega. Learn by heart this equation as well. I think you guys understood the derivation. Write down these things up to here. Then we'll do some questions. We'll do some questions. To write down it. You write down. If you finish copying down, raise your hands. Okay. Right. Okay. Okay. Question number one. SQ2. SQ2. Write down. Question. Now this is somewhat good question. Okay. Uh, Find the omega of corresponding SHM. Find the omega of corresponding SHM. Find omega of corresponding SHM. Look at it. Number one, A equals minus 9x. A equals minus 9x. Number two, A equals minus 5x. Number three, 2x equals minus 80. Number four, 2a equals minus 50, 5 squared, 10 to the power minus 2x. Quickly copy down this question, copy down. Then we'll write next question as well. Right, question number 2, write down next question. Sorry, SQ3 ni, sample question 3 ni. SQ3, write down. 3m is minus 1 and 3m is minus 1 and 3m is minus 1 and 4m is minus 1 are velocities. 4m is minus 1 are velocities corresponding to the displacement 8 centimeter and 6 centimeter respectively. 8 centimeter and 6 centimeter respectively. Find the time period of the motion. Find the time period of the motion. Quickly do these two questions. How about if you started doing SQ2, raise your hand? Started doing SQ2, raise your hand. Okay. Raise your hands. How many of you finished doing SQ2? Raise your hand. How many of you finished doing SQ2? Raise your hands. Now it's very easy, right? Now we want to find what now? In the question they're asking, we want to find. We need to find the omega. We need to find omega. Very easy. How many of you found omega? Raise your hand. First one, a equals minus 9x. How many of you found omega? Hands up. How many of you found? No one? There's only two? Yeah. It's not difficult. Now we know that a equals minus omega squared x. We know the equation for characteristic equation of simple harmonic motion. A equals what? A equals minus omega squared x. That's the equation. Right? So then here, 9 means what? Omega squared. Yeah, 9 means omega squared. Therefore, you can write down what? Omega squared equals 9. What is omega value? Therefore, omega equals 3 rads per second, radian per second. Then here, what is the omega value? Second one, omega squared equals 5. That means omega equals root 5 radian per second. You find what is the value of root 5? Rad per second. It's not difficult. Then this one, third one. Now 2x equals minus 8a. If I subject a equals minus 104, 104x. Then what is my omega squared? Here omega squared is 104. Omega squared equals 104. Therefore, my omega value is how much? Half. Half means what? 0.5. If I take root in both sides, omega means what? Half. 0.5 radian per second. What about the last one? Fourth one? Subject A. If I subject simply in this case, if I divide both sides by 2, if I divide both sides by 2, 2 cancel out. 50 over 2 means 25. 25 5 squared minus 2 simple x. This entire one is omega squared. This entire one is omega squared. So therefore I can say my omega squared as what? Omega squared equals, look at it, omega squared equals 25 5 squared minus 2. If I take root in both sides, I can write down omega equals what? 5 minus 1. Therefore 0.5. What is the value of 5? 3.14. If not 2207. Simplify this, you will get the answer. I think you guys understand this one. Next question. How many of you started doing next question? Raise your hands. How many of you started doing next question? Raise your hands. Start doing next question. Raise your hands. Next one. That is a good, but without drawing a sketch, it will be very difficult, right? Just draw a sketch and start to think. Just draw a sketch. Then you will understand. Draw a sketch. So if I do that question also, 3 ms minus 1, 4 ms minus 1 are velocities corresponding to the displacement 8 centimeter and 6 centimeter respectively. Find the time period. Now I can find the time period if I found the omega value. Because time period capital T equals 2.5 omega. If I can find omega, I can find time period. Now they have given velocities at two different instants. Look at 3 ms minus 1, 4 ms minus 1. Now they have given velocities at two different instants. That means two different displacements. 3 ms minus 1 belongs to 8 centimeters. 4 ms minus 1 belongs to 6 centimeters. Right? Then they have given simple x values and v values. Then what is the equation that we learned for instantaneous velocities at different instants? V squared equals omega squared inside the bracket a squared minus x squared. That's the equation that we learned actually. So you want to write down two simultaneous equations. Then you get the answer. If I draw the diagram, next question. Okay, if I draw the diagram, look at it. SQ3. Right. Let's say this point is equilibrium point. Equilibrium point is point capital low. Equilibrium point is point capital low. When displacement is 8 centimeters and 6 centimeters. Right? Displacement is 8 centimeters, 6 centimeters. Look at it. When your displacement is 6 centimeters, when your displacement is 6 centimeters, x equals 6 centimeters. They have given velocity of the object is how much? 4 ms minus 1. Velocity of the object is how much? 4 ms minus 1. Very carefully listen. Let's say object is moving this direction. It's completely alright. One can consider moving this direction. No, moving that direction, no issue. Velocity is how much? Velocity is 4 ms minus 1. When the displacement is 8 centimeters. When the displacement is 8 centimeters, proper diagram will make you for the final answer. When the displacement is 8 centimeters, then they have given velocity is how much? Velocity is, then velocity is how much? 4 ms minus 1. Then velocity is 4 ms minus 1. Then you want to understand amplitude is when you consider amplitude of this motion, because now the velocity is 4. Sorry, my bad. The velocity must be 3. Okay, my bad. 3 ms minus 1. Okay. Then you want to understand now amplitude will be larger than 8 centimeters, right? Because amplitude means velocity becomes 0. Then somewhere here velocity is 0. 0 velocity is increasing 3, 4. It's not important. Now for this instant, you can apply what equation? We can apply that equation v squared equals omega squared a squared minus x squared. That equation. So we know this equation. V squared means omega squared a squared minus x squared equation. For this instant, if you apply this equation, velocity is 4. Omega you don't know actually. If you know omega value, then if you can find this omega value, then you can find the time period. So your target is find is omega actually. Your target is find is omega. Inside the bracket, you don't know a as well actually. You don't know a as well. Minus x is displacement corresponding to 4 ms minus velocity is 6 centimeters. When you convert to meters, 6 into minus 2 whole squared. This is your equation 1. Right? How many of you understood up to here? Raise your hands. Raise your hands. How many of you understood up to here? There is nothing difficult. Okay, then when you apply the same equation for this instant, here 4 squared, here 4 squared. When you apply this for this instant, 3 squared, velocity is 3 squared. Again, you don't know omega. Omega squared Inside the bracket, you don't know amplitude as well, A squared minus, this time displacement is how much? 8 centimeters to meters minus 2 whole squared, equation 2. Now there are different, there are two unknowns, capital A and capital omega. There are two unknowns. You have two equations. So therefore, when you simplify these two equations, you will get the answer, right? But the problem is depends on the approach that you select. You can end up quickly. If not, you might take some time to do this. So one can do something like this. One can divide these two equations. One can eliminate omega. But you want to understand, we want to find actually omega. One can eliminate omega and one can find amplitude and then they can find omega. But it's a long process, right? So what I thought do is, now there are different ways, okay? But what I thought is, I thought of expand these brackets. Then what will happen? 16 equals, from equation 1 I can say 16 equals a squared omega squared minus, now 6 minus 2 means 0.06 whole squared, 0.06 whole squared omega squared. I see this as my equation 1 dash. Very similar from my equation 2, 3 squared means 9, 9 equals a squared omega squared inside the bracket, sorry, a squared omega squared minus 8 minus 2 means 0.08 whole squared, 0.08 whole squared omega squared, equation 2 dash. Then someone tell me what is the best operation. Now I want to find omega actually. If I could find omega, problem solved. Now someone put in the chat box, what will be the best option? Best operation? Anyone? What is the best operation? Yeah, leave a reply. Leave a reply, best operation. Not addition. What is the best operation? O level maths. O level maths. What is the best operation? Huh? Subtraction. If you subtract 1 dash minus 2 dash, you can cancel out a square omega square terms. Then only remaining is omega square. Subtraction. So when I subtract 1 dash minus 2 dash, then I will get what? 16 minus 9 equals a square omega squared cancel out. Then I am getting minus 0.06 squared omega squared minus 0.08 squared omega squared, 0.08 squared omega squared. If you subtract, you will get something like this. Then 16 minus 9 means here it will be 7. 0.06 square means how much? 0.06 means how much? 6 square means 36. Then 36 minus 4, something like that. I end up with something like that. If I take square of this 0.06 whole square means 6 minus 2 whole square is 36 minus 4 omega squared. But there is minus, okay? Forget this minus. Plus 0.08 square means how much? 64 minus 4 omega squared. Omega squared. Then I can add these two. 64 plus 36, 100. Am I correct? No, my bad. 64 minus 36. 64 minus 36 how much? 40, 50, 60, 28 minus 4 omega squared. So when I substitute omega squared, I am getting 7 over 28 minus 4. If I I can divide 7 here, it's 1, here it's 4. If I take root in both sides, I will get 1 over 2 minus 2 omega. If I take root in both sides, 1 over 4 means 1 over 2, minus 4 means minus 2. Minus 2 will become 100 if I bring the numerator. 100 over 2 means how much? 50 rad per second is my omega value. But I don't want to find omega actually. I want to find the time period. What you want to do? We know that T equals 2 5 over omega. Then 2, what is the value of 5? 3.14. Omega is 50. Then you will get the answer. How many of you understood the answer? Understood? Raise your hands. How many of you understood? I think most of you understood. I think. Raise your hands properly. How many of you understood? Yeah, copy down that one quickly. Copy down. Quickly copy down. Copy down quickly. If you finish writing, raise your hands. If you finish writing, raise your hands. Then I think now today we covered plenty of things today, but next day we are now still we had to do a few more theory parts today actually. I will do few more things also today. And next day we are starting with what? Corresponding circular motion of simple harmonic motion next day onwards. But this online classes, the thing is now, unlike in now, a physical classes that is obviously more interactive, that's true. But normally now in physical classes, we not continuously, usually I teach, but sometimes because sometimes we might waste plenty of time, but when someone is coming through online, whatever the theory that we covered in 4.5 hours in physical class, we can cover directly in online class. But there are some, but sometimes if the reason behind that is I give time for the students to try the questions in my physical classes, because I always think that students they need time actually, because now anyone can understand. Now when I explain this question in this way, after my explanation I know that anyone can understand. Now this is how we approach the question. But the most important thing is, if I give this question, student wants to do this question at that time. So usually in my physical classes, what I do, I give so much time. So I give sometimes 5 10 minutes, sometimes even I give more time, because it's in one's perspective it seems like a waste of time, but I feel that there is a benefit for every student if I give a time. So Because of that, sometimes whatever the theory that we cover in 4.5 hours in theory class, we can cover within 3 hours in online classes. But covering theory is not always the important thing. So whatever the question I give, you must be able to get the answers. But in online class, usually I don't give so much time. We can't give so much time as well. Because in online class, we can't waste time. Because I don't so much think about uh, time. I don't so much think about the questions that you can do in the class. Because we have a limited time, 3 hours. Because I can't do an online class for 4.5 hours. I know that it's not effective. So maximum 3.5 hours. But if it is compulsory, I might do 4 hours. But I don't go beyond 4 hours because no, it's an online class. Right? Sometimes I might do if it is compulsory, I will do. But so therefore, I say that now there are benefits in online class. There are some drawbacks in online class as well. But overall, it's so much beneficial online classes. Because when you're comparing the time that you spend for traveling and the expenses, forget about the expenses, especially for a student, much important thing is time actually. So therefore, the students can save the time. So I believe that that's the best thing happens in these online classes. But the difficult thing, the drawback is now you guys in a physical class under one teacher's supervision, you guys try to pay your attention. Even you feel very lazy or even you are feeling very tired, you somehow you pay the attention until class finishes. You somehow you keep attention. But sometimes in online classes, unless you have a dedicated attention, then most of students they just eagerly waiting when will I stop the class. Then for now, always I say that these A levels only for the students who would really like to work actually. These A level classes are only for the students who wants to work, who work actually. So these math science streams only for the students who wants to work, who wants to go for results. For others, these online classes or any these A classes, physics, math science classes, not suitable for them. If you genuinely work, if you genuinely work, obviously you can go for results. It's up to you. One important thing I say for a student who is doing math science stream is consistency. Consistency. When someone's goal, if not dream, if not target, where is the time that student cannot reach that student's expected result, right? One student must have consistency and commitment because in entire this 2.5 year A level life, that student must be committed to A levels. Number one priority is A levels. When someone is doing these math science streams, I'm talking about math science streams. I don't mind about other subjects. When someone is doing math science streams, that student must entirely commit that student's life for this A levels. Number one priority is tuition, classes, schools, studying at home. That's the number one priority. So when someone is doing other, it's okay to do what other activities. When one student can't balance it, I would say that stop doing all other activities. If your plan is going to this education, if you have planned to enter local universities, that is your hope, then stop all other activities and keep on focusing these A levels. Right? Because different students are in different financial backgrounds. Because one student can balance other activities and education as well. But for some students, even they got fail or even they got poor results in their A levels because of their financial background. They are able to go for higher studies, very quality higher studies in foreign abroad countries. So therefore, I'm not talking about the people who are in good financial condition. Talking about the students who really go for higher studies through these local universities. So therefore, always give 100% effort. Commit, give your commitment to these A levels. Keep on working, then you can achieve. Right? Okay. Then next topic. Next topic. Now we'll draw two graphs and we are stopping. Okay. We'll draw two graphs and we are stopping. Okay. Subtopic: variation of acceleration of an object. Variation of acceleration of an object in SHM with displacement. Variation of acceleration of an object in SHM with displacement. Now draw the graph. Draw the graph. Variation of acceleration with displacement in SHM. Draw the graph. How would be the graph? If you draw the graph, how would be the graph? Right now. This time your y-axis is acceleration. Your x-axis is what? Displacement. Y-axis acceleration. X-axis displacement. Okay, x-axis displacement. Displacement simple x. Draw the graph quickly. Now we learn that characteristic equation. Now we know that acceleration equals minus omega squared simple x. Then your y x-axis is your displacement x, then minus omega, your gradient simply y equals mx graph. Sorry, y equals minus mx graph. Draw the graph. Now displacement is maximum at the say negative amplitude minus a. Draw the graph. Negative amplitude minus a. Draw the graph. How would the graph? Is your minus a. Minus capital y equals minus mx graph. So maximum acceleration, let's say somewhere here. Exactly, acceleration is maximum. Minimum acceleration belongs to, let's say, somewhere here. Acceleration maximum a max plus a max, a negative maximum acceleration. Negative maximum acceleration a max, negative a max. If you draw the graph, how would the graph? Graph would be like this. Am I correct? Graph would be like this. Draw it. Draw it quickly. The next topic. Raise your hand. Somebody finish drawing. Finish drawing. Raise your hands. Quickly, quickly. Draw it. Draw it. Quickly. Finish drawing. Right. Next topic. Variation of force of an object in SHM. Variation of force of an object in SHM with displacement. Quickly. Variation of force of an object in SHM with displacement. Now draw that one. So when you apply F equals ma for the object moving in a simple harmonic motion, look at it. F equals ma. Now if force, mass, simple limb, acceleration, we know that minus omega squared x. Minus omega squared x. Am I correct? And then I can write down force equals what? Minus simple m omega squared simple x. This time I this time I my x-axis displacement. This is my y. This is my x minus m omega squared. My gradient. I say it's m dash or something. Y equals minus n mx. Same graph. So f max will be something here. F max. Yeah, same graph. Same graph. Do that one also. Quickly. Write on this one also, okay? Right. Graph, look at it. Now the summary. Let's say now this object is at amplitude plus a. Negative amplitude minus a. Now we know that it is zero. Velocity is zero. Exactly the amplitude velocity is zero. Then positive amplitude to equilibrium point, velocity is increasing. Look at it. Velocity size of the arrow represents the magnitude of the velocity. Velocity exact point, velocity is maximum. Velocity is maximum at the equilibrium point. Then velocity is decreasing. Exactly at the negative amplitude, velocity is zero. Again, velocity a simple harmonic motion. Again, velocity at the equilibrium point, velocity is maximum. Again, velocity decreasing. Velocity is zero. You understand? I think you understand this thing. What? Now, complete is very careful understanding simple harmonic motion. Point. Velocity with at the force of acceleration both are same. And equilibrium point. It's very important thing. If I mark the maximum at the amplitude, acceleration maximum, then acceleration is getting decreased. Exactly at the center, acceleration is 0. Acceleration is decreasing. Acceleration is towards the object is increasing. Same thing for this motion also. Raise your hands. How many of you understood I explained? Now do this diagram. Important, not important. Write down. When object moves in a simple harmonic motion, velocity equilibrium point. Velocity is maximum at the equilibrium point. Velocity is maximum at the equilibrium point. It's lagging. It's lagging.